So in this example, we're supposed to sketch the function f of x equals x times the factor x minus 3 times the factor x plus 2. We're supposed to sketch it using its roots. Now, a sketch is a general shape, not necessarily the exact function. So we're going to be using the specific characteristic they tell us to use to actually sketch it. Since they're telling us to use the roots, we'll start off by finding them. Roots are x-intercepts or solutions when set equal to 0. So if I set the equation equal to 0, zero product property says I set each individual factor equal to 0. So I'm going to start off with x equals 0, x minus 3 equals 0, and x plus 2 equals 0. I'll next solve each of those equations, adding 3 to both sides for the second one, giving us x equals 3, and subtracting 2 from the third one, giving us x equals negative 2, meaning I have 3 roots, 0, 3, and negative 2. I'm going to next kind of sketch a graph. I find having the little sketch of the graph is just kind of nice. We're actually getting started with the sketch, that is, because that's our overall goal in this example. I find this helpful for the next part of the problem. So just labeling 1, 2, 3, 4, negative 1, negative 2, negative 3, and negative 4. Our x-intercepts are at 0, 3, and negative 2. Now, we need another property here to figure out whether the actual more details of the graph. So in order to do that, since we have roots or x-intercepts, we're going to use a property that's connected to it, which is positive and negative, just whether the function is above or below the x-axis. So as I do this, I'm going to split my graph up like I've done in the past. This gives me 4 separate intervals, negative infinity to negative 2, negative 2 to 0, 0 to 3, and 3 to infinity. And I'm going to have to check on each of these intervals whether it's positive or negative. We can do this just by plugging into the equation using a test point. So what I'm going to do is I'm going to make a chart here off to the side, and because this has a factored form to it, it's actually easier if we just look at the individual factors rather than looking at the entire equation as a whole. So what I'm going to do is I'm going to take each of my intervals, negative infinity to negative 2, negative 2 to 0, 0 to 3, and 3 to infinity. And I'm going to pick a test point or an x value on each of those intervals to use to tell whether it's positive or negative. So on the first interval, I'm going to use x equals negative 5. The second interval, I'm going to use x equals negative 1 because it's between negative 2 and 0. I'm going to use x equals 1 on the third interval and x equals 5 on the last interval. Okay, so we have that part of the chart kind of set up here. And this is the type of chart. You make a very similar chart in calculus a lot if you go on to take calculus with positive, negative, or increasing, decreasing. But what we'll do is we're going to look at each kind of factor here. So x is one of our factors. X minus 3 is the second factor. And then x plus 2 is the third factor. And then we want to look at the overall result. Now, we only care if the overall result is positive or negative, so we don't actually need to record the numbers. We just need to record whether it's positive or negative, because when we multiply everything together here, we can easily figure out the signs. So if I go through that first one as my first example, I'm plugging in negative 5 in for x. Well, that would just give us negative 5, which all I care about is the negative part. And the second factor, if I plug negative 5 in, negative 5 minus 3 is negative 8, which again, all I care about is whether it's positive or negative. And then if I plug negative 5 into the third part, Well, that would be negative 5 plus 2, which is negative 3, so it's negative. Now this works very nicely because we're talking about factors. Different story if we don't have the factor version. But because we're talking about factors, we're just multiplying these three separate values together. So we have a negative times a negative, which creates a positive, and that positive times our third negative means the overall result is negative. I don't need to actually know the y value here. Since we're just doing a sketch of the graph, that y value isn't exactly needed. We don't know where the extremas are in each of these intervals, so we're just using a reference of whether it's above or below the x-axis as I go to sketch my graph. I'm going to go ahead and repeat the same process, but first I'm just going to make a note that since it's negative, I know that this function is going to be down below the x-axis. So I know it's going to be down here. Somewhere down there. Okay, so I know it's going to be below the x-axis. Next, I'm going to do the same thing for the next interval. My negative 1 is my test value, so I'll plug it in. Negative 1 in for the x will just be negative. Negative 1 minus 3 for the second round would be negative 4, so negative. Then negative 1 plus 2 would be positive. A negative times a negative is a positive, and that positive times our last positive will result in positive. Since I know that it's positive, I know that it's going to be above the x-axis, which means it will be up here in this area here. Okay, so then we go through with each of the remaining intervals. So my next point is 1. So 1 into x will just be positive 1, so positive. 1 minus 3 is negative 2, and 1 plus 2 is positive 3. Then we have a positive times a negative, which is a negative, and then that negative times a positive is overall a negative, meaning that this interval, it will be below the x-axis once again. So I've highlighted that region, and now we have one more here to go through and do. Our last one, if I plug my 5 in, 5 in for x will just be positive 5. 5 minus 3 will be positive 2. Then 5 plus 2 will be positive 7. Positive times a positive results overall in a positive, meaning this last region will be above the x-axis. Okay, so there we have it. Our graph will be in each of those shaded regions based on our table here. So now we just have to draw something in that will kind of match that. So it's going to be going up through that point, curve down. And as I said, this is a sketch just using the key values of roots. So this is not going to be 100% accurate. Your humps here in the middle might be higher up, they might be lower. Since we're not really focused on the actual y value and just drawing a sketch, that's not a big deal as to where those humps get to their highest or lowest or extrema points. Okay, in this example, we have more of a demonstration. We're asked, how does the multiplicity of a 0 affect the graph of the polynomial? So multiplicity, remember, means that a factor is occurring more than one time in the factored form of the expression. So here you can see I have a Desmos graph pulled up. Right now we have two factors, the factor x minus 1 and then the factor x plus 2. The factor x plus 2 has an exponent of a, which is set up as a slider so that I can change the number of times that it occurs. So the x minus 1 here is only going to happen one time in this expression, and currently the x plus 2 is only happening one time. So as far as the roots or zeros that goes with it, x minus 1 affects this root over here at positive 1, and x plus 2 has a root of negative 2. Remember, the roots and the factors have the opposite signs. Now what I'm going to do is I'm going to change this slider, and I should have set this up better ahead of time, but I'm going to change my step to 1. I'm going to start it at 1 and go to, I think 6 will be enough. So as I drag this through, you're going to notice some stuff happens. So if I change it to 2, you'll notice that the root at 1 still has the same basic shape, goes straight through the line. But you'll notice it no longer goes through right here. I'm going to continue to go through and change it further. So I'm going to go to 3. You'll see it has changed back now. You see we are going through the x-axis. This one, the x minus 1, the root from the x minus 1 is still doing the same thing, going straight through. But right now the x plus 2, as I change its multiplicity, its connected root is changing, or the shape of the graph is changing at its connected root. If I continue to go through and do it more, you'll see now it no longer goes through at -2. It once again stops there. If I increase it to 5, again it goes through. And 6, it no longer goes through as well. It gets very, very flat right there at -2. So what we can conclude from this is that if a factor or a root has an odd multiplicity, it goes through the graph, or not through the graph, through the x-axis, versus if the multiplicity is even, it just touches the x-axis. Or is also referred to as tangent. Tangent to the x-axis. So that's the characteristic with multiplicity and how it affects the graph of the polynomial. Okay, so in this example, we're supposed to write the equation for a 4th degree polynomial using its roots from the graph below. So now it's very important to understand that if it is a 4th degree polynomial, that means the most roots it can have is 4. This means that includes multiplicity and complex roots as well. This particular example is not focused on complex roots. We're just focused on real roots. So it will include multiplicity. So we should have at most 4 roots. And we will have exactly 4 roots if we count multiplicity and complex roots. So roots are also referred to as x-intercepts. So you can see we have one x-intercept is x equals -1. We have another x-intercept of 1. And we have another x-intercept at 2. However, for specifically the one at 2, you'll notice its shape is different as it relates to the x-axis. At -1 and +1, it goes through the x-axis, but at x equals 2, it just touches the x-axis or is tangent to the x-axis. That means this one occurs an even number of times. That's going to be important in a second. So I'm going to go ahead and rewrite these as their factored form. If x equals -1, that means, turning it into the factors, we would just move everything to one side and get x plus 1 equals 0. In other words, the first factor is x plus 1. For the second root, we would do the same thing. So we'd have x minus 1 equals 0, which means our second factor is x minus 1. And our third factor, or a third root, is x equals 2, so we'll subtract 2, giving us x minus 2 equals 0. So x minus 2. Now I did say that we should have up to 4 roots, including multiplicity, and I know that x equals 2 has to occur an even number of times. Now as far as roots go, when you're listing the roots, multiplicity doesn't affect what you list as the roots, but it does affect the factors. In order for it to have an even multiplicity, that means that factor, the corresponding factor, must have an even exponent. But our degree can't be higher than 4, and currently we would have a degree 3, so I know this would just have to be 2. That's the only possible even number that would give us a total of 4 roots. We can't have more than 4. We can have 4 or less. Right now we have 3 visible roots. The only even number that I could use is 2 to make a total of 4. So this one is occurring twice. And sometimes that's a little bit of a guess and check process to figure out the exact number of which roots occur how many times, depending on the graph. But yeah, there we have it. And since we're writing an equation, we want to make sure to put y equals or f of x equals. I'm just going to use y equals here. So here is my equation. It doesn't specify standard form, so we can just leave it like this. But if it asks for standard form, we just distribute everything out. Okay, in this example, we are asked what are all the real and complex zeros of the polynomial function shown in the graph below. Now, before I start actually doing this, I'm going to just analyze my equation real quick. You'll notice this equation right here, this function right here, its highest exponent is 3, making it a third degree polynomial. Since it is third degree, that means, according to the fundamental theorem of algebra, we will have exactly 3 roots if we count multiplicity and complex roots. So by the time I'm done, I should have a total of 3 solutions. Now, we're going to start by looking at the graph. So if we look at my graph, I can see I have 1 root visible on the graph, and I know that this root occurs an odd number of times. Whether it's occurring 1 time or 3 times, that's not necessarily clear. I could probably assume based on this shape, it's only occurring 1 time. But it's not always clear just by looking at this, but I can tell I have a factor or a root of x equals 2 as one of my 3 roots. So in order to figure out the other ones, I'm going to use synthetic division and either try to factor or try quadratic formula. So I know one of my roots is 2. I still need 2 more. So I'm going to go ahead and do synthetic division. You could also do long division as well. So my root is 2. Remember, when you're doing synthetic division, you use the root. Long division, you use the factor. So right now we have coefficients of 1x to the third, negative 1x squared, negative 1x, and negative 2. We'll drop our first number down, and we're ready to go. For synthetic division, we do 2 steps. We multiply our numbers to get 2, and then we add vertically to get 1. Multiply our numbers. 2 times 1 is 2. Add vertically, we get 1 again. Multiply 2 times 1, we get 2. Add, we get 0. Our remainder is 0, which we should know because 2 was a factor, so we should have known 0 was our remainder. If we didn't get 0 for the remainder, then we did something wrong. It's guaranteed to be 0 because we knew from the graph that 2 was the root. But that leaves us with 1x squared plus 1x plus 1. We still have to find the remaining roots of this. Now, if I try to factor this, multiply first and last, we're not going to be able to find a combination of factors that adds to be the middle term. So instead, we're going to use quadratic formula. Since we can't find the factors, or since we can't factor it, I know our roots are either irrational or complex. So we're going to have to use quadratic formula. So negative b plus or minus square root b squared minus 4ac all over 2a. And a, b, and c in this case are all 1s. All the coefficients are 1s here, so I'm just going to go ahead and plug stuff in. So we have negative 1 plus or minus the square root of 1 squared minus 4 times 1 times 1 all over 2 times 1. If I go through and simplify, so we have negative 1 plus or minus the square root of 1 squared minus 4 times 1 should give me negative 3 if I go through and simplify that, over 2 times 1, which is 2. We have a negative underneath the radical, so we're going to try to break it down here. Since we have it negative, we'll separate the negative 1. And 3 is not a perfect square, and there are no perfect squares that are helpful that go into 3. So we'll leave it as 1 times 3, or negative 1 times 3. So overall, we have negative 1 plus or minus, square root of negative 1 is I, radical 3 over 2. And there we have it. These are our two roots, because remember the plus minus sign in this formula or in the quadratic formula means that there are two solutions. So we have two roots here and then one root from the two earlier. So overall our answers are 2, put them in squiggly bracket because we have a list here, negative 1 plus I radical 3 over 2, and negative 1 minus I radical 3 over 2. And there we go. Okay, in this example, we're going to use the graph to help write the function in factored form. When we write it in factored form, it's very similar to when we're finding the roots, except we don't actually apply quadratic formula if we can't factor it further. So just like before, I'm going to look at my graph for any roots that I can actually tell what they are. I can see I have these two roots here, but I'm not quite sure what they are. I do know I should have a total of 4 roots. And I do know that this is also root at x equals 3. That one's definitely, sorry, x equals negative 3. That one's very clear that it's x equals negative 3. But the other two, I can't exactly tell where they land. So I'm just going to have to go with what I know here and start with x equals negative 3. Based on the shape of the graph, I can see that it touches the x-axis and then curves away. It doesn't actually go through at negative 3, which means that root has an even multiplicity. So it has to occur 0 times, 2 times, 4 times, 6 times, and so on. But based on the fact that I have 2 clear roots, that means since we can only have a total of 4 roots, it can't occur 6 times, can't occur 4 times because we already have 2, and it obviously doesn't occur 0 times because we can see it. So I know based on just elimination here that it has to occur 2 times. Cool. With that, we can go ahead and start doing synthetic division to reduce this polynomial and then try to figure out what the remaining 2 factors are. So we're going to do synthetic division. So negative 3 is my root. My coefficients is 1x to the 4th, 6x to the 3rd, 7x squared, negative 12x to the 1st, and then my constant term is negative 18. Going through synthetic division, we'll multiply and then add, multiply to get negative 9, add giving us negative 2, multiply negative 3 and negative 2 to get 6, add gives me negative 6, multiply gives us positive 18, and add gives us 0. Again, remember that that remainder should be 0 because I know that negative 3 is a factor, or is a root. I also know that negative 3 is a root twice, so I'm going to go ahead and divide again by the negative 3. My coefficients now will be these numbers. If I want, I can write it out as 1x to the 3rd plus 3x squared minus 2x minus 6. But we're going to go ahead and synthetically divide it again, just because of the multiplicity that is apparent on the graph. So going through the same process, drop the 1 down, we'll multiply, 3 plus negative 3 is 0, multiply, giving us 0, add gives us -2, multiply again gives us 6, and our remainder is once again 0. If I did not get 0, I either made a mistake or I did something wrong with the multiplicity, but it's clearly occurring an even number of times, so I know I had to do this twice with the -3. But this now reduces the degree down to a squared. So we are down to 1x squared, in other words, just x squared, plus 0x minus 2. Okay, now our goal here is to factor and not to solve. If I were to solve this, I could set it equal to 0 and just do reverse order of operations, but my goal is not to solve on this one, it's to factor. So, can I factor x squared minus 2? Well, we can't factor x squared minus 2 unless we're going to talk about like factors with the square root. I know I can't factor it because it has the two terms. There's no common monomial, and 2 is not a perfect square. So because of those reasons, I can't factor x squared minus 2. So x squared minus 2 is one of my factors. My other factors, and I do have more factors, come from this root of x minus 3. Well, if x minus 3 is the root, then the corresponding factor is x plus 3. Remember, the roots and the factors have the opposite signs. So we have one factor of x squared minus 2, one factor of x plus 3, but we also know that the factor of x plus 3 has a multiplicity of 2 based on the shape of the graph and the fact that when I divided by -3, we got the remainder of 0 twice. So overall, this is the factored form of f of x. So in this example, we are going to be solving the equation 2x to the third plus 5x squared minus 3x equals 3x to the third plus 8x squared plus 1. Now there's a couple of different ways to do this. I'm just going to approach it the simplest way possible, and we are doing it graphically for this. In order to do this one graphically, we simply just graph each side of the equation. We've done it before. So I'm just going to graph each side of the equation as its own equation. So 2x equals 2x to the third. We have plus 5x to the second. We got minus 3x. So there's the first side. And this works with handheld graphing calculators, not just Desmos. The same idea. So the other side is y equals 3x to the third plus 8x squared plus 1. So those are the two graphs. And now once we have it graphed, we just look for the intersections. There is just a single intersection on this one at -1. -1 comma 6.000. But because our original equation just has a single variable, we are just interested in the x value. So the answer is x equals -1. Sometimes with the polynomial functions, it can be easy to miss solutions. So another option for this type of equation, when you're solving it via the graph, is to move everything to one side. So if I were to move everything to one side, I would end up with, possibly, depending on which side I moved stuff to, I would end up with -1x to the third minus 3x squared minus 3x minus 1 equal to 0. So the other way of doing it is moving everything to one side and then graphing just this side and finding the x-intercepts, which are the zeros. And you would see that we would get the same thing, which I am going to actually type that in. So if I got to actually use this right. So if I actually type that in and just verify it, we have -1. Got to hit the equals, -1x to the third. I did not do a very good job of writing the 3. Minus 3x squared. Minus 3x. And minus 1. So you can see it there, and we're just focusing on that green one. You can see that the green one only hits the x-axis one time at -1, which is the same solution that we got when we graphed each side as its own equation. So regardless of which approach you take graphically, you'll get the same answer of x equals -1. Okay, in this example, we're going to be solving or finding the solutions for the inequality x to the third minus 16x is less than 0. We're going to be doing it graphically. In order to do graphically, we're going to take kind of the same approach as the previous one. We're going to graph both sides as its own equation. So we're going to have one side as y equals x to the third minus 16x. And it's not actually typing. X to the third minus 16x. Y equals. Okay, so there's the first side. The other side is 0, which is actually the x-axis. So in this case, I don't have to graph it. But I'm going to graph y equals 0 anyways, because it will hopefully make it stand out a little bit nicer. So y equals 0. So there we go. So we have the two sides graphed. Now we are just making a comparison. We're going to look at this graph, and it's going to be the intersections, split the graph into different regions here, like we have done for positive and negative in the past. We're doing now. So we have a couple different regions. Now this is going to be a little bit different from positive and negative, but we are split from the region negative infinity until this x value, which is -4. But what makes us different from positive and negative is when we did intervals of positive and negative, we always put parentheses. However, for this type of problem, it's not necessarily going to be parentheses. Sometimes it's the square bracket. Whether it's a square bracket or parenthesis for the interval depends on what the inequality sign is. Since it's just a less than, that means we're going to be using the parentheses. If it was less than or equal to, we would be using the square brackets for everything except the infinities, because again, we cannot reach infinity. So in this case, we will be using the parentheses. So for my next interval, it will be -4 to 0. Then from 0 to, it looks like +4. And then from +4 to infinity. Now our answer isn't all of these. We're looking for specific regions. So we are looking for specifically where our current function is less than 0, which means it's going to be lower than 0, or in this case, lower than the x-axis. So let's see, where's my highlighter? So if we look at the first region, here is where the graph is in the first region. And you can see that it's below that blue line, which is our second line, which is our y-intercept. So this region, it's negative. The middle region, you can see it's above, so it's positive. Then we have below again, and then above again. We are looking for where our function is less than the blue line, so lower than the blue line. Okay, so that means the first region's interval, which was negative infinity to -4, and the third region, interval, which was from 0 to 4, are the solutions. Any numbers on that interval would be a solution to the inequality. I'm not exactly sure where my intervals down here went. They kind of vanished on me, but whatever. Okay, in this example, we're going to actually be solving that same inequality, but we're going to be solving it algebraically. So if I'm solving this inequality algebraically, what I'm going to start by doing is basically find the x-intercepts, just like what we looked at on the previous one. So if it wasn't already a 0 on the one side, we would have to move everything to one side first to actually go about doing this problem. So as I go through and do this, since it's already everything on one side, I'm just going to take my inequality, turn it into the equation, because we want to find where it's equal to 0 first. I'm going to go ahead and factor this expression. So first of all, there's a common monomial in both terms. So I'm going to pull out x, which will give me x squared minus 16. And then x squared minus 16 is a perfect square pattern. It's the difference of squares. It's that a squared minus b squared pattern. So according to the factors, its factors are a plus b and a minus b. So in our case, our factors are going to be the x from earlier, and x plus 4, as well as x minus 4. From the zero product property, we'll set each of these factors equal to 0 and solve so that we actually have the roots. So we have x equals 0, x plus 4 equals 0, which would give us a root of x equals negative 4, and x minus 4 equals 0, which will give us a root of x equals 4. So we have 3 roots, but those aren't the actual answers. We just need them. Now I'm going to represent this graph a little bit graphically anyways, just because it kind of helps me picture things out as I try to go about doing this. So just like we saw graphically, we still have our 3 x-intercepts. And those x-intercepts still divides my graph or my function into 4 different regions. Negative infinity until negative 4, negative 4 to 0, 0 to 4, and then 4 to infinity. Parentheses with the infinities, and again, just like when we did it graphically, because this is the less than sign, we will be using parentheses for all the other ones. If it was less than or equal to, we would use the square brackets instead. Now, unlike previously, we don't have a graph to actually figure this out with. So instead of a graph, we'll have to use just some algebraic approach. So we're just going to pick some test numbers on each of the intervals and just plug them in to see whether it's negative or positive. So I'm going to pick x equals negative 5 here for the first region. I'm going to do x equals negative 1 for the second region, x equals 1, and then x equals 5 for the other region. Now that we have our test numbers picked out, we have to plug them into the equation and just figure out whether it's positive and negative. And just like before, we are looking for the negative ones because we are looking for less than 0. So looking for negative. Okay, so I'm going to go ahead and plug each of my test numbers into my function. I can use either the original function or one of the factored versions. It is typically easier to use the factored version because all we care about is whether the overall result is positive or negative. So I'm going to use the factored version here, and I'm going to make a little chart kind of like what I did in the previous, in one of the previous examples. So we have our factors x, x plus 4, and then x minus 4, and then we have the overall result of x times x plus 4 and x minus 4. Just going to make a quick chart. So my first x value for the test was x equals negative 5. If I plug negative 5 into the first factor, it's going to give me a negative number. The second factor, negative 5 plus 4, is negative 1, so that would be negative. And then negative 5 minus 4 is negative 9, so negative. Negative times a negative times a negative is overall a negative. So my first test number makes it negative. So that means my graph will be down below. So the interval negative infinity to -4, non-inclusive, will be one of the solutions for this inequality. Any number on that interval would solve the inequality. My next test number was -4 to 0. Or, sorry, that was the interval. The next test number I have is x equals -1. If I plug -1 into the first factor, I'm going to have a negative. -1 plus 4 is a +3. -1 minus 4 is a -5. And then a negative times a positive times a negative is overall a positive. So that's going to be up above, which means it's not going to be one of the solutions we're looking for. We are looking for solutions where it's less than 0. I have two more to quickly go through. We have x equals 1. If I plug 1 in, the first one will be positive. 1 plus 4 is +5. 1 minus 4 is -3. So a positive times a positive times a negative overall is negative. And then that means this one is below, which is what we're looking for. So 0 to 4 is also a solution, as we found graphically. And if I jump through the last one here, we have x equals 5. Plugging 5 in, we have positive. 5 plus 4 is +9. 5 minus 4 is +1. A positive times a positive times a positive is positive, which means it is above the x-axis on this interval. We are looking for the negative ones, so this last interval would not work as well. So the solution, just as we found graphically, are these two intervals here.